All right, welcome everyone. So we're going to get started. Today we're going to finish up talking about linearization, and then we'll start talking about Lhopitals Rule, so an application of derivatives that will allow us to kind of calculate some more complicated limits. So we'll see that in just a few minutes. But for right now, we're going to finish up talking about linearization. So we left off kind of looking at, what are the applications? Where is linearization used? And we were talking about, in physics, the linearization of the sine function is often used to simplify the model for a swinging pendulum or periodic motion. So we looked at that kind of discussion last time. In this example, we're just going to calculate the linearization of sine of x at x equals 0. So what is the linearization? Essentially, it's the tangent line. So with the tangent line, there's three things we need. We need the x coordinate of our point, we need the y coordinate, and we need the slope. And to calculate the slope, we need the derivative. So let's start by just first writing down the derivative of sine of x. And this one we should just know. It's cosine x. And we're going to we want to find all those pieces. So we want the x coordinate, we want the y coordinate, and we want the slope for our tangent line, essentially. So what is our x coordinate? Well, we're given that. It's that a value, a equals 0. So the x coordinate is 0 here. Now to find the y coordinate, this is where we take our x coordinate and we plug it into our original function. So we're going to evaluate our original function at 0 in this case, and sine of 0 is just 0. Now what about our slope? Well, to find the slope of our tangent line, this is where we take our derivative and we plug in the x coordinate. So our x coordinate was 0, so we're going to evaluate f prime at 0. And when we plug 0 into the cosine function, we get 1. So we have all three ingredients that we need for our tangent line. So we just use the point slope formula for the tangent line. Y minus our y coordinate is equal to m times x minus our x coordinate. So that's just the point slope formula. Let's put in the pieces. So y coordinate is 0, our slope is 1, and our x coordinate is 0. And if we just clean that up, we end up with the line y equals x. So our linearization of this function at a equals 0 is just the function x. So this is our linearization. And really all that was different here is we were just giving it a special name. We were calling it L of x. And so what this really says is that for x values near a equals 0, our sine function, sine of x, is approximately equal to x. And so this is often called the small angle approximation. So you'll probably see it at some point if you're taking physics or even engineering course. You'll probably see this small angle approximation at some point. And this is where it comes from. It's the linearization of the sine function near at a equals 0. All right, so that's just one example. So linearizations are often used to simplify mathematical models. Let's look at one more example. And in this one, we're going to find the linearization of the function y equals f of x at the point 2, 1, where function f is implicitly defined by the curve y to the power 5 plus 3x squared times y squared plus 5x to the power 4 equal to 93. So in this example, and we'll talk more about it once we actually go through finding the tangent line, but in this example, it's impossible to actually solve for y. So we can never actually find a nice formula y equals blah 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 x terms. So we can never actually solve for y. There's actually a function out there that y is equal to, because we can implicitly define y as a function of x, but this equation is just impossible to solve. So a linearization is sort of our best option here, or is an option for getting a formula for function y. And that's what we're going to see. So let's actually go through the steps here. And we want to find the linearization of this function. So it involves going through our three ingredients. Find the x-coordinate, find the y-coordinate, find the slope. So we're given the point, we're given the x-coordinate, we're given the y-coordinate. We just need to figure out the slope, and that means we need to figure out dy dx. So because this is implicitly defined function, we're going to have to use implicit differentiation. So let's see what this looks like. So let's remember how implicit differentiation works. We write down our equation, y to the power 5 plus 3x squared times y squared plus 5x to the power 4 equal to 93. And then we go through and we apply the derivative to every single term. So we're going to differentiate the y to the power 5. We'll differentiate the 3x squared times y squared, our 5x to the 4th, and then we differentiate the right-hand side as well. Now for most of these, it's pretty straightforward. The only one that might be a little tricky is this one in the middle here, and we'll need product rule for that. So let's see what we get when we go through the differentiation. So first we'll start with that y to the power 5. So we do the power rule like usual. So we get 5y to the power 4. But because we're differentiating a y term, we multiply the result by y prime. Then we go through and let's do the product rule for that next term. So 3x squared times y squared, we'll just write down the product twice, 3x squared times y squared, and then we apply the derivative to, in the first copy, we apply the derivative to the first part, and then in the second copy, we apply the derivative to the second part. So that's product rule. And then let's keep going. We're going to differentiate that 5x to the power 4. That's just power rule. So we get 20x times x cubed. And then on the right-hand side, when we differentiate the constant, we get 0. All right, so a little bit more differentiation there. So let's keep going. So we use the product rule, but we still have a little bit more to do. So derivative of 3x squared, just basic power rule. We get 6x. Then we have the derivative of y squared, basic power rule. So we get 2 times y, and then because we differentiated a y term there, we multiply the result by y prime, and then we have our plus 20x cubed equal to 0. So this gives us an equation then that we can solve for y prime. So that's the next step, is we want to solve this for y prime. So I won't go through the whole, all the steps to solve it for y prime. But what you want to do is you want to kind of go through and keep all the terms with y prime, get them all to one side. And then any term without y prime, you want to move to the other side of the equation. So if we solve for y prime here, we end up with negative 20x cubed plus 6xy squared, and I'll put the negative in front, divided by 5y to the fourth plus 6x squared y. So I skipped a couple steps there, which you'd want to show. So I'll leave it for you to check to finish those steps to solving for y prime. But that's what we get. We get negative 20x cubed plus 6x times y squared over 5y to the fourth plus 6x squared y. So we found dy dx. So in step 2, we're going to use that then to calculate our slope. So this should start feeling like the exam question on the last exam was very similar to this. You had to calculate the derivative, and then you had to evaluate it at the point to find the slope of the tangent line. So that's what we're doing in step 2. Step 1, we found the derivative. There it is. Now in step 2, we're going to find the slope by evaluating at the point. So our slope m is the derivative dy dx, where we're going to evaluate this when x is equal to 2 and when y is equal to 1. So wherever we see an x, we're just going to plug in 2. So we're going to get 20 times 2 cubed plus 6 times 2. And then wherever we see a y, we're going to plug in 1. So we get 6 times 2 times 1 squared all over 5 times 1 to the fourth plus 6 times 2 squared times 1. And doing the arithmetic, we end up with negative 172 over 29. And we'll just leave that as a fraction. So we found the slope of our tangent line at this point. So we have our x-coordinate, we're given that. We have our y-coordinate, we were given that. And now we calculated our slope. So the final step in finding this linearization is to just put all those pieces together and figure out the tangent line. And we'll do this one, kind of talk through this one a little bit differently. So let's write down the formula for linearization L of x. Really, this is just the point slope formula where we've solved for y. So here's our linearization. F of a, this is really our y-coordinate. F prime of a, this is our slope. And then a, that's our x-coordinate. So that's where the linearization formula comes from. Really, it's just the equation of our tangent line, which comes from the point slope formula. And so let's fill in all the ingredients. We know what all those pieces are, so let's figure out what the linearization L of x is. So our y-coordinate is 1. Our slope, we said, was negative 172 over 29. So we fill that in. And then our x-coordinate was 2. So x minus 2. If we simplify, we can do a little bit of arithmetic there. We end up with 373 over 29 minus 172 over 29 times x. So just distributing the slope there and combining like terms. So there's our linearization, and let's just mention again, we briefly talked about it, but this equation is it's actually impossible to solve for a nice formula for exactly what y is. So here, y equals f of x is impossible. Can't do it. We can't get a nice formula for exactly what function y is. So the best we can do is just with that implicit definition of y. So we don't know what the formula for function f of x is. We know it's out there, but it's actually impossible to solve for explicitly. But near x equals 2, if we use this linearization, and let's write it as f of x. F of x is approximately equal to 373 over 29 minus 172 over 29 times x. So even though technically speaking that function f of x is impossible to solve for explicitly, we can get the linearization. We can get a pretty good approximation of what that function is doing near x equals 2. All right, so that's just another application of linearization here. Is sometimes, most of the problems we look at, we have these nice functions f of x, but in a lot of applications, there is no nice function f of x. And so the linearization is the best that we can do. All right. So let's move into Lhopitals Rule. And looks like there might be a couple questions. Maybe double check me on this, but I believe the double negative here would make this term positive in front. So that 373 over 29 is positive. And then if we get a common denominator, so I didn't show all the steps here, but if we get a common denominator, we could write this positive 1 as 29 over 29. And so I think if you go through the arithmetic, you should end up with, when you combine all the constant terms, you should end up with 373 over 29. Yeah, so double check me. I'm pretty sure. But, maybe there's an arithmetic error there, but I'm pretty sure if you get the common denominator, you should end up with 373 over 29. All right. So let's go into Lhopitals Rule, and we're going to talk more about indeterminate forms for limits. So that's going to be kind of the key to our discussion here. And let's start by talking about quotients. So this is where in all the limit problems, it was quotients that gave us the most trouble. And the reason is because we could have division by 0. And as soon as we get division by 0, that's where a lot of interesting behavior happens, but it also makes things more complicated. So a lot of the limit problems that we've done in the past all involved limits where the denominator went to 0. We get interesting behavior, but it comes at a price. It makes the limit more complicated. So let's say we want to calculate the limit of some function f of x divided by some other function g of x. And for this little discussion, we're just going to assume provided both of these limits exist. So both the limit of the top function as x goes to a and the limit of the bottom function as x goes to a, they all exist. So we really need to see what happens to our term in the denominator. So case 1, the term in the denominator does not go to 0. So the limit of g of x does not equal 0. This is fine. We can handle this. This one's no problem. So what we can use is we can use our quotient limit law. So if the denominator does not go to 0, then there's really no issue. So what did the quotient limit law say? Well, it said if we had some function f of x divided by some other function g of x, we could just break that limit up and look at the limit of the top function, look at the limit of the bottom function, and we would get some number as our answer. So this would equal some number. So So there's really no issue there. So that one's good. If we don't have division by 0, then it's fine. Where things get interesting, though, of course, is case 2, where the denominator, where the limit of the bottom term does go to 0. And then it kind of breaks down further into 2 subcases based on what the numerator does. So if the numerator does not go to 0, well, then what happens? We would get the term in the top, f, is not going to 0, but the term in the denominator is going to 0. So we would get what we called our c over 0 form. And this we saw way back towards the beginning of the course. This is an infinite limit. So the limit of f of x over g of x as x goes to a would be either equal to plus infinity or minus infinity, and it would be up to us to decide what figure it out. So we'd use a test number, plug the test number into the function, and see if it's a positive value or a negative value, and that would tell us if it's plus infinity or minus infinity. So if the numerator does not go to 0, but the denominator does, then it's an infinite limit. Now, if both terms go to 0, we're going to get what we call, and we've looked at this a little bit before, we call this the 0 over 0 form. And this is where we ran into trouble, and we called this an indeterminate form. And so it's unknown what actually happens. Does the limit exist? Is it infinite? Is it some number? Is it 0? We don't know what this limit is doing, so it's a mystery. And so the 0 over 0 form, if you go back to a lot of what we did in our limit topics, the 0 over 0 form is one of the most common types of limits that we worked with. And we had a whole bag of tricks that we did. We would factor and cancel. We would use the conjugate method. We would do common denominators. We had a whole slew of algebraic tricks that allowed us to kind of figure out what the limit was doing. And we're going to add to that in just a second. So we're going to add to our bag of tricks. But let's first look at another indeterminate form, or just we'll kind of formally define these gadgets. So we say that the limit of f of x over g of x is an indeterminate form of type 0 over 0 if both the limit of the numerator and the limit of the denominator both are 0. And then similarly, we have an indeterminate form of type infinity over infinity where the limit of the top function and the limit of the bottom function are both plus or minus infinity. So on this page, we're describing really, there's a few different types of indeterminate forms here. There's 0 over 0, and then that second one with infinity over infinity, it kind of covers a bunch of cases. So we might have like infinity over infinity, minus infinity over infinity, infinity over minus infinity, or just negative infinity over negative infinity. And so, these are all fundamentally very similar. So we just call these infinity over infinity form. So we don't really distinguish between all those little special cases there. We just call it an infinity over infinity form. All right, so why are these indeterminate? Why don't we know? Well, there's sort of a conflict between the numerator and the denominator. So in the 0 over 0 form, if the top function wins, so if the numerator kind of overpowers the term in the denominator, what happens to our overall limit is that it goes to 0. If the bottom function wins, in this case, well then what happens is the limit becomes infinite. So it's either plus infinity or minus infinity. Or another option is the two functions sort of balance out. So the top function and the bottom function sort of balance out, and that's one more possibility. So it really depends on what those specific functions are. We can't say what's happening in general. And so we don't know. There's a mystery here. Same thing with the infinite over infinity form. There's a conflict between the top function and the bottom function. So in this case, if the top function wins, then it gets really big positive or really big negative. If the bottom function wins, well then when the denominator gets really large and sort of dominates the fraction, what happens to the fraction is it gets really close to 0. And so the overall limit in this case would go to 0. Or again, another option, third option, is that the two functions sort of balance each other out, and we end up with just some number in the middle. So it's really unknown what's happening for these indeterminate forms, and so we have to dig a little bit deeper and kind of try out some different techniques. And that's what we're going to see next. And then just a quick comment there at the bottom. We've defined these indeterminate forms for limits as x goes to a, but there's similar definitions for the right-hand and left-hand limit, or limits at positive or minus infinity. So there's similar definitions for each of those other cases. All right, so the rule that we're going to use, which will allow us to really handle a lot of these indeterminate quotients, is called Lhopitals Rule. So if we have an indeterminate form of type 0 over 0 or infinity over infinity, then the limit of that quotient, the limit of f of x over g of x, is equal to the limit of f prime of x divided by g prime of x, provided that second limit there exists or is infinite. So this rule, just a couple comments here, this rule also works if we talk about right-hand limits or left-hand limits, or limits as x goes to infinity or limits as x goes to minus infinity. So a similar rule exists for each of those. And so this rule is going to help us calculate the limit of f of x over g of x. And there's going to be a temptation here to kind of mix up Lhopitals rule and the quotient rule. We don't want to do that. These are very different things. So the quotient rule, let's just remember, the quotient rule tells us how to calculate the derivative of f of x over g of x. So this is one of our derivative rules. And Lhopitals rule allows us to calculate the limit of f of x over g of x. So something completely different. So we're going to be calculating the limit of f of x over g of x as x goes to a. So the quotient rule, that's one of our derivative rules that allows us to do the derivative of a quotient, of a fraction, f of x over g of x. In Lhopitals rule, we're interested in calculating a limit. So you just want to make sure we keep those two different rules clear in our head. So one is for calculating derivatives, the other one is for calculating limits. All right, so let's see how this works in practice. So let's try an example. So we're going to do the limit of natural log x over x minus 1 as x approaches 1. And so the first thing we should do whenever we are presented with a limit is we should really just try plugging in. So we're going to start by just trying, we're going to try our quotient limit law. So quotient rules for derivatives, quotient limit law, what does that do? Well, it allows us to split up the limit into the top and to the bottom of our function here, fraction. And we're doing the limit as x approaches 1. So just try and split up the limit over the fraction and then just plug in. So we get the natural log of 1 over 1 minus 1. So we're just evaluating here. Why are we evaluating? Well, natural log is continuous, x minus 1 is continuous, so we can just plug in to evaluate those limits. Now the issue happens because natural log of 1 is 0, and 1 minus 1 is also 0, so we get the 0 over 0 form. So that's indeterminate, so that tells us we have to stop with this approach. We can't just plug in to get our limit here. But as soon as we see that 0 over 0 form, it tells us we can use Lhopitals rule. So this does actually tell us something, though. It tells us that we can use this new rule. So that's what we try next. So we tried just using our quotient limit law and evaluating. Didn't work out. But we see that we can use Lhopitals rule, so that's what we try next. All right, so let's write down the limit that we're trying to do. Limit of natural log x over x minus 1 as x approaches 1. And let's see how we actually implement the rule. So what do? Well, we keep our limit the same, and then we just apply the derivative to the function in the top, and we apply the derivative to the function in the bottom. So we're going to calculate those derivatives. And that's where we actually apply the rule. As soon as we do the derivative of the top, derivative of the bottom, that's us applying Lhopitals rule. So we'll just write a little h there to indicate that's where we've used the Lhopitals rule. And so I'll just mention it for exams and when you're doing the homework. You should get into the habit of writing that. So that's something we'll be looking for, is make sure you specify when you use Lhopitals rule. If you're doing a limit and you use Lhopitals rule, make sure you indicate where you apply the rule. So you can just mark it with a little h like that over the equal sign, and that's fine. All right, so let's calculate the limits. So we're going to do the limit as x approaches 1. And let's do the derivative. So derivative of natural log x is just 1 over x. Derivative of x minus 1 is just 1. And so what we have here is this expression, and we can simplify it down a little bit. So as soon as you do those derivatives, try to simplify the result down a little bit before you keep going with the limit. So that's what we're going to do. We're going to simplify. So try to simplify this down. So, we don't normally write multiplication by 1 or division by 1, so we could just simply write this as the limit of 1 over x as x approaches 1. And now that function is continuous at x equals 1, so we can just plug in and see what we get. So we get 1 over 1 if we plug in, and then if we simplify, we get 1. So as soon as you go through this step of simplifying, what you end up with is a brand new limit. So this is a brand new limit that we're presented with here. And so what we should try immediately after we simplify and we have this nice shiny new brand new limit, we should try plugging in and see what we get. So basically every time we apply Lhopitals rule, once you're done with the derivatives, try plugging in to see what you get. And if you get a number like we do here, well then there it is. That's your answer. All right, so let's try another one. Let's do the limit of sine of x over 1 minus cosine of x as x approaches pi from the left. So first thing, we're presented with the limit of a quotient. Let's just try plugging in to see what we get. So that's our first step. We're going to try using the quotient limit law. So we'll write this as the limit of sine of x as x approaches pi from the left divided by the limit of 1 minus cosine of x as x approaches pi from the left. Let's plug in. So we're just going to plug pi into each of those. So we get sine of pi on the top. We get 1 minus cosine of pi in the denominator. And we should know what sine of pi is. It's 0. And we should know what cosine of pi is. It's -1. So we end up with 0 over 1 minus -1, which is 0 over 2, which is not indeterminate. So 0 over 0 is indeterminate, but 0 over 2 is perfectly fine. We can divide 0 by any non-zero number, and we get 0 as a result. So that's our answer. We tried our quotient limit law. We were able to plug in because each of those functions, sine and 1 minus cosine, are continuous. And the result that we get is a perfectly good number. So that's our answer. So this is just a bit of a warning here. You have to go through this first step of checking to see if the limit is actually indeterminate, because it might not be. So if the limit is not indeterminate, then Lhopitals rule doesn't work. And you'd get the incorrect answer. So if the limit is not indeterminate, that means we cannot use Lhopitals rule. So when you're doing this in the homework, when you're doing it on an exam, we want to see that first step where you actually check to confirm that the limit is indeterminate or it's not indeterminate. So you need to show that as part of your work. Can't just jump right to Lhopitals rule because it doesn't always apply. And that's what this example is showing, is you do have to go through that first step of checking to see if the limit just exists. And if it does, then you're done. You don't even have to use Lhopitals rule. All right, let's keep practicing. So it's always good to practice. Let's try another one. We're going to do the limit of e to the x over x squared as x approaches infinity. So first step, just like we mentioned, you got to check it. So we're going to check using the quotient limit law. So let's split up our limit, look at the top, look at the bottom, and this is as x goes to infinity in both cases. So what is the limit of e to the x? E to the x just by itself, what does that limit do? Well, e to the x gets really large as the exponent gets really large. And then x squared, as x gets really large, x squared also gets really large. So we end up with an infinity over infinity form. So that's not the answer. We're not done. So that's not the answer, but it actually does tell us a little bit of something. It tells us that we can use Lhopitals rule. So let's apply the rule. So we've verified that it's in the correct format. This is a indeterminate form, 0 over 0 or infinity over infinity. Those are the only two forms where Lhopitals rule directly applies. So it's in the right format. So now let's apply the rule. So this is, in case anyone was wondering, L'Hopital is it's named after a mathematician from hundreds of years ago, but this is someone's name. So in case anyone was interested or wondering, why do we call it L'Hopital's rule? It's named after someone. All right, so let's apply the rule here. So we're going to do the limit of e to the x over x squared as x approaches infinity. Let's apply the rule. So what does that do? Well, we apply the derivative to the function in the top, apply the derivative to the function in the bottom, and that's where we've actually applied L'Hopital's rule. So let's put a little h over the equal sign there just to indicate that that's where we're applying the rule. Yeah, so it is pronounced L'Hopital. So it looks like hospital, but it is pronounced L'Hopital. So just a little pronunciation there. All right. Let's continue on. And we've applied the rule. Let's do the derivatives. So let's see what we get. So derivative of e to the x is just e to the x. That's a nice one. Derivative of x squared is 2x. And really, there's not too much to simplify here. So all we need to do is we have a brand new limit. This is a brand new limit. So we should check it again. As soon as we do the derivatives really change the behavior of our function. And so really they're going to be simplifying it down, hopefully. And what we should do as soon as we calculate those derivatives is check to see what's happening. And so just like we did in the previous step, let's look at the limit of the numerator. So limit of e to the x, that's still going to infinity. Limit of 2x as x goes to infinity also is going to infinity. And we see we have another indeterminate form. So it got us somewhere, but we're still not right where we need to be. We're still at an indeterminate form. So we apply the rule again. So let's write down what we have. We're going to apply the rule again. So we'll differentiate the top, differentiate the bottom, and this is us applying the rule. So let's mark it with a little h just to indicate that we're applying Lhopitals rule there. Let's calculate those derivatives. So derivative of e to the x, that's our nice one. That's just e to the x. And then derivative of 2x, also nice, just 2. And now we have a brand new limit. Not much to really simplify there. So we try just seeing what happens and see, check to see if we get another indeterminate form. But in this case, we don't, because the limit of e to the x is just, it goes to infinity. So the limit of e to the x divided by 2 is infinite. And so that's our answer. It's not an indeterminate form. So when it's just an infinite limit, that really describes what's happening. The function is just getting really large positive. We know what's happening to our function. Indeterminate means there's some mystery there. We don't really know what our function is doing. So we don't know what our fraction is doing. But with an infinite limit, if it's infinity or minus infinity, there's really not much mystery there. We know exactly what it's doing. It's blowing up, getting really big, large positive, or getting large negative. All right, so this is an example where we actually had to apply Lhopitals rule twice. All right, let's try another. Let's look at the limit of natural log x over the cube root of x as x goes to infinity. First step, we got to check it. So we're going to check with the Quotient Limit Law. So let's look at what the limit of the top function is doing and the limit of what the bottom function is doing. And these are limits as x goes to infinity. And so limit of natural log x as x goes to infinity, well, that goes to infinity. And then the limit of a root function as x goes to infinity also goes to infinity. So we've checked it. This is an indeterminate form of the right format, infinity over infinity. So that's not our answer. That doesn't tell us what's happening. It's unclear. But it does tell us that we can use Lhopitals rule. All right, so that's the next step. Let's apply the rule. All right, so we have our limit that we're interested in, the limit of natural log x, and we're going to be doing derivatives. So instead of writing the cube root of x, I'm going to write that as x to the 1/3 power. So let's apply Lhopitals rule, and we're going to do the derivative of the top, do the derivative of the bottom, and let's fill those in. So we'll do the derivative of the top, derivative of the bottom, and that's where we've actually applied the rule. So just put a little h there to indicate, or you could write it all out, but just indicate where you apply the rule. Now let's do the derivative. So derivative of the top function is 1 over x. And then the derivative of the bottom function, just power rule, so it's 1/3 x to the negative 2/3, if we apply the power rule there. Now we have this brand new limit, but before we try plugging in again, we want to try to simplify it down as much as possible. So let's try simplifying this. And in the denominator there, we see a term with a negative exponent. So let's try to cancel that off. And actually, let's try to cancel off all those terms in the denominator. So we're going to multiply by a fancy 1. So how could we cancel off the 1/3? Well, if we were to multiply it by 3, that would cancel it off. So anything that we do in the denominator, we can't change our function here, so we'll have to do the same thing in the numerator. So we'll multiply the numerator by 3. And then we want to cancel that x to the negative 2/3 off. We're trying to simplify this down. So in order to cancel that off, we could multiply by x raised to the positive 2/3. So anything that we do to the denominator, we have to do the exact same thing to the numerator. So we're multiplying by a fancy 1 in order to simplify this down a little bit. And let's see, we multiply the 3 with the 1/3, those cancel. We multiply the x to the positive 2/3 with the x to the negative 2/3, those cancel. And we'll take this 3x to the 2/3 and we'll multiply it into the numerator there with our 1 over x. So this simplifies down a little bit into the limit as x goes to infinity of 3x to the 2/3 divided by x. And we can go a little bit further simplifying. So we can cancel off some of the x terms there until we get 3 over x raised to the 1/3 power. And this is the limit as x goes to infinity. And that's something we can do. So when we have 3 over a power of x, or a non-zero constant over a power of x, this is equal to 0. So there's our limit. And why is this the case? Well, we really have one of our c over infinity forms. And we saw this back in our limits section with limits at infinity. This was a common form. And we know that those are equal to 0. Yeah, that's I wanted to mention. Notice that in all of these examples, we're using the limit notation all the way through the problem. So, this is something that I've tried stressing in the exams. It's something that we're actively grading for, and I want to make sure everyone does it consistently, is consistently using that limit notation throughout all your work. And then once you actually calculate what the limit is equal to, we don't write the limit of 0, we drop the limit sign. So at this very last step, we're actually saying what the limit is equal to. So just a little note here with the notation. So we would not say the limit of 0 over, we wouldn't write this as that last step. We've actually calculated the limit. So as soon as we calculate the limit, we drop the limit notation. But throughout all of our work, we have that limit as x goes to infinity in front of all of those expressions. And then we get to the very last step where we actually say, all right, this is what our limit is equal to. And at that point, that's where we stop writing the limit sign. So we would not write the limit of 0 as x goes to infinity as our answer. The answer is just 0. So just a little bit about notation. That's part of the course is discussing limits. So want to make sure that you understand the notation, when to apply it, when not to apply it, that sort of thing. All right, let's try another one. So let's do the limit of tangent x minus x over x cubed as x goes to 0. And first step, we're presented with a limit. We have no idea what's happening, so just try plugging in x equals 0 and see what you get. So that's the first step. First step is to check. So let's look at the limit of the top function, limit of tangent x minus x as x goes to 0. Let's look at the limit of the bottom function, x cubed as x goes to 0. Tangent x, if we plug in, well, tangent is 0, or tangent of 0 is 0, so we end up with a 0 over 0 form. So that's not our answer, but it does give us a little bit of idea what we can do. We can use Lhopitals Rule. So we can use the rule. So that's our next step. We've checked it. We see that it actually is an indeterminate form. So the next step is to apply the rule. All right, so let's fill that in. So we're doing the limit of tangent x minus x over x cubed as x goes to 0. We're going to apply h here. So we're going to differentiate the top, differentiate the bottom function. So let's fill what those are. Tangent x minus x over x cubed as x goes to 0. Derivative of tangent x is just secant squared. Derivative of negative x is just minus 1. And then derivative of x cubed is 3x squared. Not too much to simplify there. So we could just check it again. So we have this brand new limit. Not much to simplify. If we want to get clever, there actually is a way to simplify it, but we'll just kind of do more of a brute force type calculation here. So we'll just check this and let's see what we get. So secant of 0 is 1, or secant of 0 is 1. So we're just plugging in to check, and secant of 0 is 1, so we get 1 minus 1 on the top. We get 0 on the bottom. So this is a 0 over 0 form. So that's not the answer, but it does tell us what we can do. We can use Lhopitals rule again. So that's what we're going to do. We're going to apply the rule again. So let's write down our secant squared x minus 1 over 3x squared. And we're doing the limit as x goes to infinity. So we're going to apply the derivative to the top function, derivative to the bottom function. And if we go through our work there, derivative of secant squared, here we have to use the general power rule. So the derivative of secant squared, we bring down the 2, keep the inside function the same, and then multiply by the derivative of secant x. And the derivative of secant x is secant x times tan x. So that's chain rule. That's the general power rule there. And then derivative of minus 1 is 0. Then in the denominator, derivative of 3x squared is just 6x. And we're doing the limit as x goes to infinity. Or, no, x goes to 0. All right, let's check those. So we have a brand new limit here. Let's check to see what's happening. So we just plug in. And if we do that here, tangent of 0 is 0. and 6x is 0, so we end up with 0 over 0 again. Another indeterminate form. So we have to try using the rule yet again. And let's not forget to mark down where we apply the rule. So we're going to apply it again. Doing the limit as x goes to 0. And I'm going to simplify the 2 times secant times secant times tan. I'm going to combine that into 2 secant squared x times tangent x all over 6x. And we're going to differentiate the top function, differentiate the bottom function. And so if we differentiate the top function, we see we have secant squared x times tangent x. We have a product. So we actually have to use the product rule there. So if we go through our product rule, won't go through all the steps, but I'll leave it for you to check. What we should end up with is 4 secant squared x times tangent squared x plus 2 secant squared x times secant squared x. And we're using the product rule there. And actually, let's just mark it up here. To differentiate secant squared, we have to use chain rule, or what we call general power rule. So to differentiate the secant squared, we have to use our chain rule. And then to differentiate secant squared x times tangent x, we have to use our product rule. And so if we go through the product rule, we should end up with 4 secant squared x times tangent squared x plus 2 secant squared x times secant squared x in the numerator there. And then the derivative of 6x is just 6. We have a brand new limit now, so we try plugging in. And when we plug in, we end up with secant of 0 is just 1. And tangent of 0 is equal to 0. So when we plug in here, we'll end up with 2 over 6. And as soon as we get a number as our answer, well, that's our answer. So as soon as it stops being an indeterminate form, that's our answer. So we had to go through Lhopitals Rule 3 times here, and eventually we got down to the point where the limit was equal to just a number, so that's our answer. So like I said, there are other ways to do this one. So we could have actually worked with this secant squared x minus 1 term. We could have simplified that down using a trig identity. But just to go through, practice using Lhopitals Rule and seeing, applying some of our more advanced differentiation techniques, chain rule, product rule, and all of that. So all of those derivative rules that we've learned, you might have to use them when you're going through calculating these limits using Lhopitals Rule. All right, so we're going to take a break just for a second talking about indeterminate quotients, and we're going to talk about an indeterminate product. So let's say we wanted to do the limit of f of x times g of x, and it turned out that the limit of f of x was 0 and the limit of g of x was either plus or minus infinity. Well, this is also an indeterminate form, and we call it an indeterminate form of type 0 times infinity. So why is it indeterminate? Well, again, there's sort of a conflict between the two pieces of our function. So there's the f of x piece, and if the f of x piece wins, then the overall product is going to go down to 0. So the overall limit would go to 0. But then there's that g of x piece that wants to get really big. So if the g of x piece were to win, well then the overall limit would go to plus or minus infinity, depending on what g is doing. And maybe neither one wins. Maybe they sort of balance out. And that's the other option. Maybe the two functions balance and the overall limit just goes to some number. So that's another possibility. So it's indeterminate because we don't know what's happening. The first function could win and the overall limit goes to 0. The second function could win and the overall limit gets really big, positive or negative, or they sort of balance out and just find some middle ground in between. So it's indeterminate. And again, we've defined this where x is going to a, but it also works for left-hand limits, right-hand limits, x approaching infinity, x approaching minus infinity, and so on. So our strategy for dealing with a lot of these indeterminate products is to rewrite the product as a quotient. And then as soon as we get it into the quotient form, we can use Lhopitals rule to kind of do the heavy lifting. So there's two ways we can go about this. When we have function f of x times g of x, we could rewrite it as a fraction where we keep that first function on top and then we put 1 over g of x into the bottom of our fraction. And so if this is the case, function f is going to 0 and then 1 over g of x would actually go to 0 as well. So 1 over g of x would be our c over infinity form, which we know goes to 0. So that's why we would get a 0 over 0 form here. And then Lhopitals rule applies. Now we have a second option. So if we have f of x times g of x, we could keep g of x in the numerator and then in the denominator put 1 over f of x. And in this case, we would get an infinity over infinity form, but Lhopitals rule also works here. And we know that 1 over f of x, if f of x is going to 0, well then we have a c over 0 form. And we know that those are either plus or minus infinity. So that's why the denominator there in this kind of clever rewrite is going to infinity. So that's the trick for how we deal with indeterminate products, is we rewrite them as sort of a fancy quotient. And we have two ways to do it, so you have to decide which way you're going to use. And sometimes one way gives you a result that you can work with and the other way doesn't. So you kind of have to decide which one to choose. So let's try it out in example 6. We're going to do the limit of square root x times natural log x as x approaches 0 from the right. And let's just check to see what's happening here. So that's always our first step. Just check to see what's happening. Look at the limit of each of the pieces. So we're going to check using our product limit law. So we're going to look at the limit of square root x as x approaches 0 from the right times the limit of natural log x as x approaches 0 from the right. And we know that the limit of square root x as x goes to 0 is 0. And we know the limit of natural log x as x goes to 0 is minus infinity. So this is indeterminate. We don't know what's happening. Does the square root function win? Or does the log function win? Or do they sort of balance out? All right, so since this is an indeterminate product, the next step, we can't go right to Lhopitals rule. We have to first rewrite this as a quotient. So that's our next step. And so we have two ways to do that. So let's try the limit of natural log x. We'll keep natural log x in the numerator, And then we're going to take that square root x and we're going to do 1 over square root x, and that's what we're going to put in the denominator. So what we've done here is essentially g of x over 1 over f of x. So just a kind of a clever rewrite as a fraction. And we're doing the limit here still as x goes to 0 from the right. And let's just check to make sure this is now a indeterminate quotient. So limit of natural log x as x goes to 0 is minus infinity. And then the 1 over square root x as x goes to 0, that's our c over 0 form. So that also goes to infinity. And so that's no good. That's not our answer. But it does tell us that now we can go ahead and use Lhopitals rule. So it's that right format, infinity over infinity, that right form. So that's our next step. All right. So we're doing the limit of natural log x. And because we're going to be doing derivatives, let's rewrite that 1 over square root x as x to the negative 1/2. So we want to rewrite that as a power function. So we'll just kind of get ahead of it there. We know we're going to be doing the derivative, so just let's rewrite it in a form that's easy to do the derivative of. So 1 over square root x is equal to x to the minus 1/2. So just a little note there. We're doing the limit as x goes to 0 from the right. So now let's apply the rule. So we're going to differentiate the top function, differentiate the bottom function. That's where we're applying the rule, so we'll just indicate that that's what we're doing. And it's the limit as x goes to 0 from the right. So let's do the derivatives now. So derivative of natural log is 1 over x. And then the derivative of x to the negative 1/2 is negative 1/2 x to the negative 3/2. And that's a brand new limit. We should try to simplify it, though, before we go further. So we're going to simplify this. And it usually helps to get rid of those terms with the negative exponent. So we want to try to cancel those off. And let's actually try to cancel off all the terms that we see in the denominator here. So to cancel off the negative 1/2, I would have to multiply by negative 2. And then to cancel off the x raised to the negative 3/2, I would have to multiply by x raised to the positive 3/2. And if I do anything to the denominator, I have to do the exact same thing to the numerator. So I'm going to multiply up here by negative 2 times x to the 3/2. Now let's see what that gives us. So in the denominator, by design, the negative 1/2 and the negative 2 cancel. And then the x to the negative 3/2 and the x to the positive 3/2, those cancel. And so what we're left with then is the limit of, and I'll take this negative 2x to the 3/2 and I'll put it into the numerator there on the 1 over x. Doing the limit as x goes to 0 from the right. And we have negative 2x to the 3/2 divided by x. Keep going. Let's clean that up just a little bit more so we can cancel some of the x's. And this simplifies down to just negative 2x to the 1/2 power as x approaches 0 from the right. And now this is a form that we can handle. So we can just plug 0 in. And we get 0. So we applied Lhopitals rule once. We simplified it down as much as we could. And then after we've simplified as much as we could, we saw that it was a form that we could just plug in to evaluate. All right, so that's an example of rewriting a product as a quotient. And we made the choice of keeping natural log on the top and then doing 1 over x in the denominator. Let's just see what would happen if we reversed it. So we do have an option here. So we could keep the square root x in the top and then do 1 over natural log x in the denominator. And we're doing the limit as x goes to 0 from the right. And what we would see is first this would be a 0 over 0 form. So we could still use Lhopitals rule, but then the issue occurs where once we start doing the derivatives, we're going to get this complicated expression. So if we were to rewrite our function as x to the 1/2 and then natural log x raised to the power -1, and we're doing the limit as x goes to 0 from the right, if we apply Lhopitals rule and differentiate each of those, so we're applying the rule there, we would get the limit of 1/2 x to the -1/2 over, and to differentiate natural log x raised to the -1 power, we have to use chain rule. So we bring down the -1, keep what's inside the parentheses exactly the same, subtract 1 from the exponent, so we get -2, and then multiply by the derivative of what's inside the parentheses, so times 1 over x. And if we were to try to simplify this down, kind of like the approach that we took in the previous case, we would end up with the limit as x goes to 0 from the right of -1/2 x to the +1/2 power times the natural log of x squared. And you can see here by looking at either of these, this looks more complicated. So if you look at either of these, Lhopitals rule looks like it's just complicating things if we use this rewrite. So that would be an indication. If you were to choose this one first and you see that after you apply the rule things are just looking more complicated, well then try rewriting the product the other way. And we saw that that way worked out. So if one rewrite doesn't work, try the other one, and that one would hopefully work. So there's a question. We'll finish up. But there's a question. Why can't we just differentiate the function as is? This square root x times natural log x. And that's because Lhopitals rule only works if it's a quotient. So 0 over 0 or infinity over infinity. So Lhopitals rule only works for those two particular indeterminate quotients. So indeterminate product, it doesn't work for right away. We have to first kind of ease our way into it. We have to first rewrite our product as a quotient. That gets it into the right format. Then we can apply Lhopitals rule. And so this example just shows that in this case, writing it as a quotient doesn't really work out too well if we were to do f of x over 1 over g of x in this case. Just gives us something more complicated, so try the other way. All right, we went over a bit. So I'm sorry about that, but we'll finish up next time. We'll look at a few more indeterminate cases. But this should be enough to really get started on most of the homework questions. And then, excuse me. And then next time we are going to start talking about our next major topic, and that is optimization. So figuring out where our function hits its maximum and minimum. So that's going to be a few weeks we'll be talking about optimization. So we'll start that on Thursday. Also, after lecture today, we'll be posting the exams. So, on Gradescope, so just have a look at those. And, if you have questions, you can go to recitation to see the solutions. If you click on each question, you should be able to see, if there's any comments from the grader, you should be able to see the comments. So just something to keep a lookout for in the next couple hours. All right, so we'll stop there. Have a good rest of your day, and then we'll see everyone on Thursday. Bye-bye.